Sabah al-Khair. I think I can still say that. It's not midday yet. So good morning, all. And I'm going to take you on a narrative about fiber sensing and the applications. And really kind of the focus here is our ability to detect tsunamis with the existing real estate that we've got out there. However, I will start by trying to describe the phenomena of the tsunami. So we have a tsunami normally occurs when there's an earthquake or a major seismic event under the sea. And not necessarily all seismic events cause a tsunami. It does require an up and down movement, a violent up and down movement, which will cause a water displacement. And as you can see on the animations we have there, as this event occurs, the water is pulled back from the beach, and then it returns back with a vengeance, you know. And as this large volume of water approaches the shore and the shallows, that's when the wave and the height of the wave and the violence manifests itself. So I think I can probably safely say that most of us are aware of the tsunami that occurred in 2004, the Indian Ocean tsunami, and the human cost that this caused. This is not part of the script, but I feel I have to share, because when it hit me personally the most was some years later. I had the opportunity to visit the Maldives, and visited one of the islands, the inhabited islands, which had a community there, a mosque, schools, and in the graveyard of the island, there were at least 15, 20 fresh graves of people that the fishermen had collected, had found floating in the sea. And it really hit me because, you know, clearly the families that lost those people do not know where they are. And they had done a fantastic job, you know, buried them with all the honors and proper. But yeah, the human cost of a tsunami. So some undersea earthquakes will, as I said, will result in a tsunami. The good thing, if you like, the positive thing is that the seismic waves move 20 to 30 times faster than the actual water wave, if you like, you know, caused by the tsunami. And so this is where we see an opportunity to devise an early warning system. So normally, we for a long time we have had seismic detectors in the land-based seismic detectors. There's a lot of them around the globe. They have a very good and sophisticated sensing suite, but the problem with them is that they are or can be rather far away from where the earthquake and the tsunami originates. And so on average, for every 200 kilometers of distance, every 200 kilometers between the earthquake, distance between the earthquake and where the sensor is located, we lose 1 minute of warning. I would like to start with some seismic detection options that we currently have. So we got the land-based detectors, Dart buoys. I'll talk in a little bit more detail to all of these techniques that we have available. So as I already mentioned, the land-based detectors easy to deploy, maintain, not that expensive, and the drawback really is they can be rather far away from where the event occurred. Then we have the Dart buoys, which they have a very good sensor suite, and but they are vulnerable. They do have to be in a hostile environment, with potentially storms and whatnot. And they are not necessarily located in the deep waters. They are generally fairly close to the shore. And so again, a little bit better than land-based detectors, but they can also have a limited warning time. Then we have the smart cables. This will be the gold standard for the telemetry in undersea cables. And the problem is there's no smart cables yet, and if they happen, it will be from 25 onwards. So there is a challenge there, and it will be a slow deployment after that. So I have here an animation of when the Fukushima earthquake struck. And you can see a typical footprint of a earthquake is you first get the P wave, S wave, which propagate from the depths through the depths of the earth, if you like, and then it is followed by far more violent what is called as a surface wave, and this is the one that moves the earth, and we feel it. And in this animation here, we have in the US, the land-based seismic detectors and the activity, how as the motion went up and down, and the activity of them, and they clearly detected the earthquake very accurately, but as we said, far away from a long way from the seismic event. We then have ocean buoys, deep ocean assessment and reporting of the tsunamis. So in terms of the Dart buoys, there has been at least 4 generations so far. So we have the first and the second generation that were deployed. They were a bit more cumbersome for deploying because what you have is the sensor suite in the buoy, and then you have a cable which is deployed down to the seabed, and they used to be deployed separately. So you needed a bit more specialized equipment and ships, in order to do that. Generations 3 and 4 are EDT, easy to deploy, and what that means is you can really launch them from any vessel, more or less. And once they go into the water, the cable, the sensor cable, auto deploys down to the down to the seafloor. And the issue again, the expensive, difficult to maintain. This is a snapshot taken on the 18th of October. So there are about 66 stations deployed. If you look at where they're deployed, it really is around the Ring of Fire, and it is a Ring of Fire. It extends all the way down to the Antarctica. So the yellow diamonds are all the Dart buoys that are operational, and they are actually providing telemetry data continuously. But the red ones are the ones that have not provided data for the past 8 hours. I assume they're out of service. And so you can see a third of the fleet has been, is out of action, if you like. So again, the issue with the buoys is they are close to the shore. Then we have the smart cables. And the acronym stands for Science Monitoring and Reliable Telecommunications. What the proposal here, the idea here is to basically in the current subsea cables repeaters to deploy sensors, a 3-axis accelerometer, and absolute pressure gauge, and calibrated temperature gauge. The issue with and as I said earlier, there will be none deployed yet until 25 if it starts the camering, which is between Lisbon, Azores. It's planned for RFS 2025. That should be a smart cable. The idea, and as we know, the region is very seismically active. Portugal, Lisbon suffered a major earthquake in the 1800s. Then we have Medusa, which is planned for 24-25, and it is meant to be a smart cable. Again, the Mediterranean is a seismically active region, as we all know. Challenges with the smart cables are the added cost, if you like, to the repeater. The other problem is with the security agencies, i.e., do they detect too much? Yes, they do. They can detect a very, very wide range of phenomena from low frequencies to rather high frequencies. The legal status, United Nations Commission on the Laws of Sea has already defined and provides legislation, if you like, in terms of the status of the subsea telecommunication cables. But at the moment, it is not clear whether the smart cables will fall under the same category, or will there be another category, which it already exists, telemetry and science monitoring section. And apparently, currently, it is completely empty. The subsea cables itself took more than 9 years to ratify. And really, provided we solve all these issues, again, we have the slow pace of the deployment. Another sensing technique we have is the digital acoustic sensing, DAS. I'll build the slide. Yeah. So we have, it is widely used apparently in the terrestrial networks. I believe that it is used very widely, especially in India and countries where there is a lot of civils activity, and there is danger to, if you like, your fiber infrastructure. The way it works is it's basically a reflectometry, OTDR type of function. It uses a very high power laser, and then detects and measures the signal behavior, from the reflections. Its limitation, its range is about 100 kilometers at best. Or if it's, in the context of the subsea solution, it will be up to the first repeater. And the other reason it is a challenge, for subsea, it does require its own fiber. You cannot have data and this high-powered laser, if you like, propagating the same fiber. Again, a very sensitive, a great sensing solution, and it does very high resolution, but short range, and it needs its own fiber. And again, the issue with how much it is detecting, and the need to maybe go through security agencies, the data first, then be filtered and then given back to you, which again will introduce delay in terms of. So then we have what we call, we have the ability to do the state of polarization measurement. This was a trial, if you like, done on the Curie cable some years ago in 21. And what you have here is basically, especially with a coherent transmission, we do have to mitigate and compensate against polarization variations. So it is a phenomenon that we already deal with. And so the idea here is to use, if you like, to check how hard is your polarization PMD compensation working, and you can detect events, seismic events or other events. You know, essentially any protuberance affecting the cable will cause an instantaneous variation in the polarization state. So we are aware that something has occurred, you know, that an event has occurred, but not really where, you know. And I personally have done a trial in Japan some years ago, which was using basically this technique to detect weather events, you know, which affected the SOP and affected the traffic ultimately for a particular customer, and then you know compensate against it. But we didn't know really where that lightning, for example, struck. We could tell that from you know the meteorological database, you know, the government database, but not, you know, from tracking the you know, from the PMD compensation in the cable. So the idea is, how do we localize? You know, can we and how do we localize the seismic event? So I think from early 2000s onwards, you know, most of the subsea cables, subsea repeaters have been with what we call a high loss loopback. And so the idea here is really most of the waves propagate through, you know, they go into the repeater, they are amplified and propagate through. There is one particular wavelength, and it is obviously was designed for telemetry purposes. Sorry, I should build, yeah. A 1561 nanometer wavelength is looped back, 99% passes onwards, and then 1% is looped back, you know, to reflect a particular pulse back so that we can monitor that. So yeah, so for this setup, you need really specialized equipment. You will need your standard telecom equipment, transponders for your own communication purposes, but then you will also need a diagnostics transponder. So you need a whole suite, a separate suite of equipment that will do, you know, will do the actual sensing, monitoring, and whatnot. So each pulse transmitted, they will be separated by 10 microseconds per kilometer. Light travels in the fiber around 4.9 5 microseconds per kilometer. So we can use the time separation to localize the effect of the seismic event. And as you can see, the setup, it is specialized equipment. This trial was done on a transatlantic cable, and interestingly enough, they picked up and recorded accurately 2 earthquakes. One was verified earthquakes. One was in Peru, magnitude 7.5, and another one in Flores Sea, 7.3 magnitude. That's in Indonesia. But you know, as I say, there is a complexity aspect with this, because you will have, especially at the CLS stations, you will have your standard operational staff, you know, that have access to you know, your telecoms equipment, and then there is another, if you like, set of transponding for sensing purposes, and yeah, it's just more expensive, more and more complex. So using the repeater loopback and OTDR sub measurements. So this is really, if you like, taking the previous trial and if you like, setup, and decosting it and simplifying it. So what you end up with is a commercial transponder which will operate and generate revenue for you, but at the same time provide you with the capability of running the diagnostics. You do have a little bit of specialist equipment, and that will be the narrowband filter and the polarimeter. And then there is no way of avoiding that, because you do need to actually assess and analyze the data separately. They are not very high cost, nevertheless. There will be a 1 rack unit of equipment, in the receiving end. So the way, the high loss loopback, and as you can see, the pulses, will each repeater, each loopback will send a pulse back, and you will have time separation of the same pulse for each repeater. Yeah, time equals distance. So in summary, then, we have a dedicated probe for the analysis, hardware and software and all the associated. We can have a dedicated commercial transponder, which will do the job. And we can have a shared commercial transponder. As I already mentioned, use an existing transponder. And the idea behind this is, I mean, for people who are not familiar with Infinera, we utilize what we call the Nyquist subcarriers. They have been a tremendous innovation in terms of enabling us to become a leader in terms of performance, optical transmission. So what we do is we utilize, we tune one of our carriers close to the 1561 nanometer wavelength, i.e. the diagnostics wavelength. We then generate a tone. From within our transponder, generate a tone next to the subcarriers. I would like to highlight that those 4 wavelengths, if you like, they are one wavelength. They are not separate wavelengths. This is the Infinera subcarriers. So we generate a tone next to the diagnostics wavelength, and then we tune that subcarrier to the HLL wavelength. So we tune it in the high loss loopback wavelength for the diagnostics purposes. This is a clean tone, which it's not modulated. The rest of that carrier, i.e. the rest of that transponder, is used for commercial traffic, just like, and so the tone acts as a probe signal, and the subcarriers carry commercial traffic. This is a trial we did with Google on the Curie cable. Curie cable is 10,200 kilometers, i.e. 105 milliseconds. And as you can see here, this is the 3 Stokes parameters of the signal. So it is a form of a COTDR function that we use. And we can see every repeater, and the effect, every span that it's having on the signal. How do we isolate the signal? Because we are sending a pulse, which is being reflected from every repeater, 110 repeaters, 110 reflections of the same pulse, and hence, 105 millisecond separacy from each pulse. But then as the pulse loops back in the second, third, and 100th repeater, you are actually observing the effect of the entire of each section. And for that purpose, we use what we call signal subtraction. And the idea is to isolate, so subtract the echo of the from the second repeater, the echo from the first repeater out of the echo from the second repeater, and then isolate each section, each span on its own, and analyze the data specifically for that span. And there is some complicated maths over there that you know do the function of the subtraction, but this is, if you like, a view of monitoring of that data, whereby, for example, at repeater 64, before the subtraction and then after the subtraction and all the events that have occurred, and this is the frequency of the change of the sub phenomena, and this is over time. And what we then found furthermore is having the sensing from both ends, so we're doing it from A to Z, and then Z to A as well, and that increases the fidelity of the data that we receive. So then I would like to take a look at the real earthquake data from the Curie trial. So this is the Curie cable, which traverses from North America to Chile, Santiago. There was the epicenter of the earthquake shown in the yellow star. That's where an earthquake struck. So you can see an event occurs on that around about the number 100, around between 6.4 and 6.6. If we zoom into that, we then see the head of the trace. Really, the highest magnitude of the variation is at the repeater 104, and you can see the other repeaters. Understandably, the other repeaters will also pick up the event, but 104 is the one that has sensed it the most, i.e., the seismic wave magnitude will have hit it the most. And this is this location here is where a land-based seismic monitoring suite was located. And you can see the distance is pretty similar between repeater 104 and the actual land-based seismic sensor. And again, the actual seismic sensor, marries really ties up well with the sensing from the repeaters, from 98 to 110. But again, 104 is the one that has detected it with the highest magnitude. So I guess, in summary, differential sub measurements do on existing submarine cables, so there is no new investment required. Those, as I said, from about early 2000s onwards, most of the subsea cables have been deployed with the high loss loopbacks. So it's easy and quick to deploy. We have shown the effectiveness of the actual trial through an actual trial. Use familiar equipment which carries commercial traffic, so no impact apart from on the receiver side, the filter and the polarimeter. So absolutely no change to the wet plant is needed. We then have several frequency. Also, yeah, very important. The frequency detection can be limited, can be controlled by the operator, so that you don't step on the toes of the security companies, i.e., Men in Black. Several trials on the way in the Atlantic and Mediterranean, and we've also working on multiple enhancements in order to increase fidelity, sensitivity, and resolution for this earthquake seismic detection. And I guess you guys have the cables, we have the technology. If anybody is interested in a trial, please let me know, and we can make it happen. And I think that's the end of my talk. Thank you. Any questions?
Hi, this is Yusuf from Omantel. My question is, this technology can be implemented in the existing, submarine cable, because should be how it will be.
So thank you, Yusuf. Yes, so absolutely, the existing infrastructure, and that's the attraction of this technology. It, as I summarized, it uses the commercial transponders. You will use, buy this transponder from Infinera to basically carry your own traffic, i.e., generate revenue for yourself. So that transponder will also provide this functionality, fiber sensing. So then you will need those extra two, polarimeter and the filter, but it's not high cost and it's not complex. And again, most of the subsea cables deployed since the early 2000s have the HLB, high loss loopback, which we described earlier. And that's what we need, in order to get the echoes from the pulses that we send down, and analyze the data and monitor it. So absolutely, all the existing, including the dispersion managed cables, from early 2000s up until 2011, 12, when we started with the dispersion unmanaged cables, which are more suitable to the coherent transmission. So yes, we can. And as I say, if you want to do a trial, we'll happily work with you.
Yeah, thank you.
Thank you.
Thank you for the amazing presentation. My question, this is Jum'a Nabi from Omantel. My question to you, you said if you want to run proof of concept, you are willing to do it. So the question is that you will run it free of charge, first question. And second question, what's exactly a requirement from our side to run this proof of concept?
Yeah, thank you very much. So yes, free of charge. Yes, we will do the trial free of charge, of course. And the requirement really is to sit down and understand, the cable, and understand your prevailing channel plan. We need to know what you've got on the cable. Obviously, make sure that once we insert the, tone, we don't interfere with the existing, traffic. And it could be more than just a fiber sensing trial. If we can also prove the Infinera line rate, if you like, performance achievable alongside the fiber sensing trial. So you know, it could be more useful than just, you know, doing one thing. We can do both.
Means that we have to have Infinera infrastructure in our network to do this.
So yeah.
If you have different provider, we cannot do it. Is that what you want to say?
No, we can. Sorry, we can. Yeah, I mean, if you go submarine cable, we would bring our trial equipment, you know, and do independently of what you've got in the network.
Thank you.
Thank
Clear.
you. So absolutely. I mean, so the question is, can we integrate? Can we run it over existing line systems, if you like? So yeah. So absolutely no issues. You know, the SLTE, you know, can be from anybody. You know, it can be Sienna, Huawei, ASN. All we need is a colorless port to access the spectrum. And this works both ways. You know, there's no issues. You know, and you know, subsea cables have been leading the open networking, if you like, for a long time. And nowadays, you know, there is a huge move in terms of what we call the open cables as well. So yeah, absolutely no issue. It really doesn't matter what you have there. All we need is a colorless port to couple in. Obviously, we will do the technical details in terms of, you know, how much power to put in and, you know, the optimal launch and all that. But ultimately, yes, no issues.
Yeah. So can we say that this is like a
Oh.
like a built-in COTDR in the SLTE, or something different? I mean.
Yeah. So absolutely, this is a COTDR function. So you looked at those three traces, the three Stokes parameters. If you square and add them, you really get the COTDR trace that you would get from a COTDR commercial COTDR solution. So absolutely, it is a COTDR type of functionality that will propagate down the entire cable length, and you know, as we showed, you know, the ability to isolate each span on its own in order to analyze the effect that each span it's having and repeater, if you like, on your signal, rather than you know, not actually knowing where the event occurred. The event occurred, but you don't know where it has occurred yet. Thank you.
Thank you very much.
Thank you.
Yeah.
Any other questions? Willie? Where's Willie? Thank you very much. An absolute pleasure. Yeah, thank you very much.